So thank you, everyone, for coming to today's CPP. Very interesting talk today. There's a lot going on in science, but one of the biggest things going on now is how we do science. And it is increasingly recognized that we must move towards more open science. There's many facets to it. It's making sure that the data are free and clear to everyone, that journals are open access and not protected by a firewall and things like that, to make sure that code is freely available to all, to look at reproducibility of results, many, many facets of open science. Now, open science, as some of you may know, is actually a part of our strategic plan for NSIDC to become recognized as a leader in open science. And we've had a number of people at NSIDC who've been really leading the charge on these. Andy Barrett, Walt Meier, Twile has been involved, others have been involved. But today, we're going to learn all about open science. How do we do it? And we have our wonderful presenters today of Andy Barrett and Walt Meier. So, Walt and Andy, the podium is yours.
Great. Thank you, Mark. Yeah, as Mark said, so today we are going to cover what open science is, but we also wanted to try and provide some more practical advice and pathways for doing this. So I'm going to lead off with a short introduction. Walt's going to talk a little more about NASA and the federal government's kind of requirements now for us to do open science, and then I'm going to kind of provide some guides to what to do with your publications and data, and then also provide some thoughts on how to get going with practicing open science. So, what is open science? Well, open science can be thought of, and there are many definitions, but one definition is that it's the opening up of the scientific process from ideation, coming up with that fantastic idea of for a proposal or project, all the way through to the results of that project. And we do this by open sharing of results, publications, presentations, along with data and code, as Mark just said. And we can start to open up all other parts of the process. There are examples where people have done an openly sharing creation of a proposal that they've then submitted to a funding agency, and you get to see all the gory details of the science being done and can access that and interact. So there's a whole range of how we can do open science. But the key part is, the idea behind this is to make science transparent and reproducible. Hopefully that produces trust from policymakers and the general public, and also to increase accessibility and participation in science. And you may well have seen this diagram in other talks, but we can break open science down into, I think, three kind of core values, if you like. Accessible, making science accessible, it's making science reproducible, and it's making it inclusive. And we do the accessibility part of it by open access to scientific publications and other information, and by opening data and sharing data and software in a fair manner, following the FAIR principles. And FAIR stands for findable, accessible, interoperable, and reusable. And I'll be going into those a little bit later. We do the reproducibility side of things by using open collaborative analysis tools. So we're working together, not as an individual or a small research group. We're working with a larger community. And we use open tools, frameworks, and libraries rather than producing our own ad hoc or artisanal kind of pieces of code to do things where possible, because those are the tools that are trusted by the community and are accessible and available to the community. And then inclusivity. We want to support diversity, equity, and belonging in science. We want to bring people who are from underrepresented groups into science and expand participation and partnerships. And we need to provide new pathways to science. There's no reason that a citizen scientist can't engage in the scientific process with us. And that should, the diversity of views and ways of knowing improves how we do science and make science more creative and addresses society's problems in more concrete ways. At least that's the hope, that's the aspiration. But science is not just an open science is not just an aspiration, right? 2023, you've probably heard, is the federal year of open science. It's also NASA's year of open science. Walt's going to be talking about some of the things that are going on there. But the White House Office of Science and Technology Policy released a memo mandating that results of federally funded research now must be open. So your publications, your data, your software, if it was produced with federal funding, needs to be open and accessible to people. And all new NASA missions and research awards must comply with NASA's open science policy, SPD 41A. Walt's going to be talking about those two things as well. So here's the outline. Walt's going to give an overview of open science initiatives. He's going to talk about some of the policy requirements that we need to meet as scientists. I'm going to talk about how we can meet those policy requirements, some of the avenues for that, and then some thoughts on implementing open science. So I'm going to hand over to Walt, and he's going to take you through the open science initiatives.
We're losing Walt. Walt, we can't hear you. Walt, we can't hear you.
Mark, he just put a comment in saying just a minute.
Oh, okay.
All right. Can you hear me now?
Yep.
Okay. Sorry, problem with my speakers and my connection. So yeah, sorry about that. So I'm going to first go through some of the major efforts, particularly if you focus on the U.S. And I would say that this is an international initiative, or not initiative. This is there's international efforts ongoing and starting to open up science, but I'll focus here on the U.S. efforts. And the first is the Year of Open Science, which is in this year, 2023, just kicking off. There was a White House memorandum, and then the NASA SPD 41A, the NASA Open Source Science Initiative, TOPS. And then also, it's not just NASA and the White House. It's really all federal agencies are being pushed to do this. NSF does have a geosciences open science ecosystem proposal call. There's a NOAA NCAR open hackathon. I'm not going to talk more about those. I'm not as familiar with those, so I'm mostly going to focus on the NASA aspects. But there are things across the federal government going towards open science. Oh, next slide, Andy, please. So yeah, Year of Open Science is kicking off in 2023. This is kind of a big push to get the federal government, the U.S. federal government, going towards open science. Shel Gentleman, who is the NASA TOPS mission lead, wrote a nice article in Nature that came out last week, I guess it was, or about a week ago, or a couple weeks ago. So I recommend taking a look at that. She has some nice thoughts on open science and why we need to do it and why it's beneficial to do it. Next slide. So yeah, last August, the White House Office of Science and Technology Policy came out with this memorandum to all the executive departments and agencies, and basically saying, we want access to be as open as possible. Publications and all data resulting from federally funded research accessible without an embargo, free and open and that they have a deadline there of December 31st, 2025. In you basically coordinating across federal agencies to make things open. So OSTP is kind of the executive branch, overall science policy group. So that this is coming from pretty much from the top, essentially from the president of the U.S. So there, like I said, there's lots of things going on. Next slide, please. And NASA, I think, is really taking a lead role in this. They came out with this Science Mission Directorate as policy document. So your classic NASA double acronym here, SPD 41A. Originally, a draft was released, I think, in 2021, and then it was open for comments and reviews, and then officially came out and was signed in this past December. So the main points are peer-reviewed publications openly available without embargo period. So this is a change from typical research publications that would be published in journals. You'd have to have a subscription. That's really starting to go away, I think. And there's going to be a big push to have these open in open journals. Research data and software shared at the time of publication or the end of the funding award. There was, I think, if I remember correctly, initial verbiage to have these out as soon as possible. And this also, I think we'll talk about this, or Andy will talk about this later. Part of the vision of open science is to make things as open and collaborative as possible. So having things out as soon as possible, even kind of in a raw form. But the SPD 41A, I think, balances that a little with some concerns by some in the community, and basically just says that the data and software have to be shared at the time of publication or at the end of the funding award. Mission data, so these are from NASA missions, data released as soon as possible, and any unrestricted mission software developed openly. There may be some software that needs to be restricted, at least for a time, but to be as open as possible. And then science workshops and meetings held openly to enable as broad participation as possible. That's something that has not typically been done. Workshops and so forth, but like science team meetings, even trying to make those as open as possible. So this is kind of the overarching goal. It's really only about a 12-page document with longer pages of appendices and other things. But I'd recommend taking a look at that, especially for anyone that's doing any NASA-funded research or working with NASA data. Next, please. So then within this, there's the NASA Open Source Science Initiative, OSSI. This is really kind of the NASA's data management strategy for in an open source environment. So it's making data open, accessible, and inclusive, and reproducible. So this is more the focus on the data side of things, and there's there's a website there for that. And so NASA data has always been open and free, but it's really about making it more accessible, more inclusive, and then also focusing on the reproducibility side as well. Next, please. And then next is the NASA TOPS initiative, Transform to Open Science. This is really, I'd say, their big effort. particularly in terms of engaging in the science community and working to help get the science community more open and getting into open science. It's a 5-year program. It's I think it's like $20 million a year to really push to educate scientists and others working with NASA data to develop open science methodologies and start working in a more open manner. There's a goal to get at least 20,000 scientists certified for open science. I'll talk about that in a moment, what that means. And there's kind of the main focus, engagement and community building. There's going to be forums, and there already have been forums and panels. Their tops have been at AGU in December, at AMS this past couple weeks ago in Denver. And it will be throughout at least the year of open science here in 2023. If you're going to like TGARS, they'll be there as well as others, and kind of there'll be a big wrap up, I think, at AGU in 2023 in December. Capacity sharing. This is really kind of developing the skills and helping scientists develop the skills through courses, curriculum, workshops, hackathons. I'll talk a bit more about this. Incentives, trying to get people to really want to do this. And they have this idea of badges, which I'll talk about it as well in a minute. But basically just kind of pushing the community as a whole towards openness. Next, please. So the strategic objectives, as I've kind of alluded to already, accelerate major scientific discoveries. So the idea here is that more open science will advance science faster and really help science discovery. So it's not just openness for the purpose of being open. It's openness towards really helping science advance faster and make discoveries. Another aspect that is important as well is when things are more open, it gives more access to historically excluded communities, communities that may not have the same resources, HBCUs, for example, and other groups that may not have the resources that big research universities have. For example, again, making journal articles and all publications open and freely accessible. Smaller colleges and smaller research groups don't necessarily have subscriptions to the different journals and oftentimes have limited access to some of the research journal articles. So making it so that everyone can access the science that's going on, regardless of what institution you're at or what group you're working with. And again, increasing the understanding and adoption of open science principles and techniques. Next, please. So, as I mentioned, AGU, had the kind of official kickoff for TOPS, although things have been in the planning stages for several months before that. The first training sessions took place at AMS in Denver here. A big focus of TOPS is this training, this OpenCore and Science Core training, which I'll talk about in a moment. They also have had an RFP last fall last fall, I guess. Rose's proposals were called for, and those proposals have been submitted and are under review currently. But there will be future calls in future years. So there's this is going to be an ongoing thing to develop curriculum and develop training. Next, please. So OpenCore is kind of their main, the TOPS main, at least initial training and curriculum to really get people trained in the basics of open science and start developing open workflows. There are 5 modules. They're about 2.5 hours each. And each module focuses on one aspect there, ethos of open science, open tools and resources, then open data, open software, and then open results. And so each of these can be taken. The first one, I believe the ethos is already out. It was introduced at AMS, and then the others will be coming out by May at the latest. And so these will be available. And go to the next one, Andy. Let's see. Yeah, go back to the previous one just real quick, just to finish that up. And so, there will be opportunities to do these modules at various conferences and workshops. There will be what they're calling virtual cohorts, where people can group together and work together virtually to go through these, or individual scientists will be able to go through these. And at the end of each of these, you'll get what they're calling a badge, which certifies that you've finished this, and then you'll have a final badge that certifies that you're fully trained in the TOPS curriculum for OpenCore. And then there'll be a science core, which I mentioned, which is still kind of under development, but it's really going to be, looking more at discipline specific areas, to focus more on specific, open science approaches to specific disciplines. So, the badges are kind of this idea of incentivizing people to do that. You can put your badge on your CV. You could include the badges in proposals that are submitted, or in promotion materials, or tenure review materials, these types of things. And the hope is, and the plan is, to try to make these a real essential part of science, and that these are, if not requirements, at least are big benefits to scientists in terms of advancing their careers and publications and promotions and so forth. So next, and there are numerous resources for TOPS. The main links here are at the top there, that kind of have links to a variety of other things. So there's a lot of stuff there. There's a nice presentation on Zenodo if you want to get more background. But I'll mention here at the end also that as the DAC scientist, one of my roles now is the TOPS DAC liaison for NSIDC, for the NSIDC DAC. So anyone interested in TOPS, feel free to reach out to me, and I'm happy to help give more information and help anyone that's interested in doing this curriculum, help connect them. I'll probably be sending out messages in the future as well about future opportunities. So next, I think that's where you take over. Okay, Andy.
Great, thanks, Walt. So those are kind of the requirements, and also the opportunities for doing open science, learning about open science. But I think there is I've certainly heard from others that there is kind of a concern that this is going to put, at least initially, some extra burden on scientists. Although I think there's definitely recognition at NASA that we can build in funding for doing open science into our proposals, and they're almost expecting that. One thing that has come up is that when we put in a new proposal for ROSES 2023, we're going to have to write a data and software management plan, open science plan, into that. Cryosphere is already kind of requiring that, but that's going to be a feature of ROSES 2023 proposals going forward. So I think what we need to think about is how we can do open science, how we can build those skills, not just by attending TOPS OpenCore workshops and hackathons, but also how we can do that within our own research groups, within our own institutions. And so before I kind of go into the details, I want to offer some kind of guiding principles, if you like. And these are my own guiding principles that are not vetted by anyone. It's just what I see and what I hear from attending a lot of things on open science. So there are many ways to do open science. We have requirements. We have to make our publications, data, and software open. But within that, there are many ways to achieve that, and there are many ways of working towards that goal. And I think as long as we remember that open science is supposed to be kind science, that's kind of a good starting point for as we kind of build our skills and our ways of collaborating. And what I mean by that is, not only are we being kind to our colleagues and the community, and to build trust and community and inclusiveness, but also that we are considerate of the people who are going to use the products of our research. So hopefully we all write papers that are open and understandable, by not only by our direct peers and experts in our own disciplines, but also we can provide information to a more general audience. But when it comes down to data, when it comes down to software, we need to be thinking about who's going to use that data and software and how they're going to use it, and are they going to be able to understand how to use it. And so I think thinking about data formats and writing good, clean, understandable software and code. I say software, but most of us just write scripts and code, right? But as long as we ensure that we're being kind to our colleagues, then I think that's a good starting point for doing open science. And remember those three core values of open science: accessible, reproducible, inclusive science. And then we have kind of perhaps more detailed ideas of following the FAIR principles. FAIR is a worldwide kind of set of principles: findable, accessible, interoperable, and reusable data and software. And I'll go into that in a little while. And I think we also need to remember that we're doing open science because we want to open up our science to the community and the public at large. But open science practices benefits us as well. One of my colleagues from NASA OpenScapes, Julie Lance, who's the director of OpenScapes, talks about doing or following workflows that onboard your future self. So, we've all come back to a project after a month, maybe after 6 months, a year. Reviews have come back and they ask us to make changes, and we're scrambling around, searching through our file systems, looking for that data file or looking for the piece of code that generated the particular plot that we need to change. Right? Workflows, open science workflows, help us kind of avoid that kind of struggle to find that information. We're able to get up and running with science a lot faster. And so I think kind of remembering these 5 points, for me, kind of reduces some of the anxiety and expectation of extra burden that open science brings. So in the next few slides, I'm going to go through kind of how do we meet the requirements, in particular of NASA, but also the upcoming federal government requirements. So making publications open. With the publication system is probably 200 years old, right? We're kind of stuck in this in this way that we have these big journals. Libraries have to get subscriptions to them, and then we can access those journals through subscriptions or membership to the societies that publish those journals. Let me get rid of that. But we can publish in open access journals. We can request that JGR or the AMS journals publish our articles as open access. That costs money, but we can write the costs of publishing in open access journals into our grants. That's something that NASA again are fully aware of. They will support the extra costs that we incur to do open science, as well as the extra time. We can also publish in a journal, not open access, but then use an institutional archive to put the actual published version of that article into it. That can be your own website. It could be, if you're NSIDC, it could be an NSIDC website. The issue at the moment is that AGU and AMS have an embargo period of 6 months before you can actually do that. But that is allowable. So that's one way to get around having to pay the extra money to have your article open access. You can also use preprint servers. There are several preprint servers out there. And this is where you submit your manuscript to a preprint server even before you've submitted it to a review. AGU suggests using the Earth Science Open Archive, and that's actually linked to JGR journals. So they're almost accommodating you putting your unreviewed manuscript up there, and once it's reviewed and accepted, a link will be put next to your article saying, hey, if you want to see the published article, this is where you go to get that. But your work is up there already. There are other Earth Archive is another preprint server, and of course Archive, which is the kind of original preprint server idea. If you're at CU, and I'm sure other universities do this, scholar.colorado.edu, which is run by the library, allows for unformatted, accepted versions of manuscripts submitted to journals to be published there. And the library will actually make sure that you are complying with the journal, so you're not running afoul of their copyright restrictions. Open access journals, preprint servers, and scholar.colorado.edu and similar services are all assign a DOI to your article. They're all searchable and they're all findable. And that's kind of a critical part of open science and meeting the FAIR principles. So using these services allows you to get your publications out there and making sure that they're open. Data is the other requirement, and journals are requiring this as well, that when we submit a manuscript, we also submit the data, either just before it's published, or, as I would prefer as a reviewer, when the manuscript gets submitted for review. So when we're submitting data, we need to make sure that the data are findable, accessible, interoperable, and reusable. We need to submit them to long-lived, publicly accessible archives. Those ensure that the data is findable and accessible. And those archives, like with the publication services, they provide services. They assign persistent identifiers to that data, DOIs. They help create metadata. You're going to have to work with people at those archives, but they're going to guide you in producing rich metadata that ensures that the data is interoperable and reusable. I've got some extra information linked at the end of this talk that highlights some of the archives that you can use. There's the Arctic Data Center, the Antarctic Data Center, NSIDC, and then there are kind of more general ones like Pangea and Zenodo as well, where you can submit your data. Putting the IR in FAIR. FAIR is not just findable and accessible, it's interoperable and reusable. And what interoperability means is that another scientist, another person can read your data using widely available tools. In order to do that, you need to be using standard formats, things like for multidimensional data, NetCDF, for remote sensing data, generally GeoTIFF, but could also be NetCDF, and then CSVs for tabular data. And if you've got more complex data structures and need to build complex data packages, HDF5 is a good one to go with. But interoperability and reusability also require that that data comes with rich metadata and following metadata conventions so that the tools you're using can understand what that data is, what the representation of that data is. And there are several kind of conventions, depending on the kind of data that you're using. There's the climate forecast or CF conventions that are widely used within neuroscience, and they generally refer to the NetCDF data format or file format. For GeoTIFFs, then the Open Geospatial Consortium provides a GeoTIFF standard for you to follow, right? These are things that ensure that you have the right geospatial coordinates, that you're using the right time formats, that you're using ways of translating row column indices into projected coordinates. The tools, there are standard tools out there that you use for writing your data into these formats, and they are often designed to provide these metadata conventions. I also say that NSIDC has put a lot of work into writing, using the CF conventions to help guide data contributors into producing rich metadata for NetCDF, and I encourage you to go and check out those resources. As I say, making data reusable means that the data and metadata are accurate, fully documented, and importantly, licensed. Generally, facts, raw data is not, you can't copyright it, but once you derive stuff from that data, then you own that copyright. You need to make sure that users of that data understand how the data can be used, and you do that by providing a license. Generally, the Creative Commons level 0 license is the one that we assign to data, and that makes for open use. You can modify the data, you can reuse it for any purposes you want. There are other licenses available, but generally the CC0 is the one that we recommend for data. Making your code open, right? This is perhaps the most anxiety-inducing thing for scientists, certainly when I sit in open science conferences and people are like, but I'm not a software programmer. My code's awful. But remember, software documents the analysis as well as allowing for reproduction of results. We can read a method section in a paper and you can get a general idea of what's been done, but it's not until you look at the software that you know what's really been done, right? How did they treat missing data? How did they do some transform to the data, or what constants did they use in some of those transforms? All right, it's the software that documents the analysis as much as anything. And I think remembering that documenting the analysis is as important, if not more important, when you make your code open than, say, allowing people to reproduce the results. I think that's a really important thing to bear in mind. You can archive that code in the same repositories as you put the data. You can put it on Zenodo or something. That code will have a DOI attached to it. That means that if someone wants to use your code, if someone wants to and cite it, and they should cite it, then you get the credit for that code. There's a lot of talk about putting code on GitHub. It's great. I think we should be using it, but GitHub is a collaborative tool. It is not an archive. And what I mean by that is that the code on GitHub can change. There can be different versions, and you can apply versions to code on GitHub. But once a change is made to that code, it's no longer tied to the data or the publication that you've also got up there. So putting your code into an archive outside of GitHub is good practice, because then you know that that specific code was used to produce the results that are provided in that paper. And you need to add a permissive license to software. The only way that science can be open, the only way that people can reuse your work is to know what the restrictions are on using that. And permissive licenses, where you allow people to copy, modify, and reuse code is the way to do that. And one thing that license says is that you can do anything to that code, but you have to give me credit for using it. And we do that by assigning a DOI to that code and having a license that goes along with it, and then that is cited in papers. I would say as reviewers, it's our job to kind of police that to some extent. Hopefully the journals are going to be providing tools for doing that, but I think as a reviewer, if you don't see a DOI for software, then you should raise that as a red flag. Okay, so sharing code, I think, is anxiety producing. We're scientists. We're generally not trained as programmers, and we have at all points in our lives written really awful, messy, confused code. I think we can counter that by, when we start off writing code, or at least kind of as we move through that writing process, we focus on clean, understandable code. And by clean, I mean that it is written in a way that you can read it easily, that you can understand it easily, you know what that person has done. Use comments, right? I think, explain what you're doing in your code. It's a document as much as it is something that you can run through a compiler and get results out of. Use descriptive variable and function names, right? Use air temperature, not T, and certainly not X and Y, right? We don't know what they are. That helps you read the code, helps you understand what it's doing. As I said at the beginning, prefer widely used packages and libraries than writing your own routines, right? One, if you write your own routine, you might have a typo in there and make a mistake. Widely used packages and libraries are being used by a whole bunch of people. They've got their eyes on it. They'll often raise issues when there's errors or problems with that code, and they will get fixed by the community. Also, other people can use those packages and libraries and recreate your work. This is not, I don't think there's a lot of talk about, well, open science means Python, means R, and non-proprietary tools. I think we should prefer those non-proprietary tools and make the effort, certainly for new graduate students, new undergraduate students, even to learn these non-proprietary tools. But I would say that clean, understandable MATLAB and IDL code is better than nothing. As I said at the beginning of the programming side of things, we're describing our analysis within the code. And so MATLAB and IDL do that just as well as anything else. And if you need to, you can take MATLAB code and write it in Python if you want. So I don't think it means that we have to give up the tools that we've spent years learning. But I think we should, if we're looking to change, use a non-proprietary tool. So those are kind of those are the steps that we need to take in order to meet the requirements of NASA. But kind of getting there and implementing that is perhaps more of a challenge. I think it requires a change in mindset. It requires learning new tools, and it requires developing new workflows. And most of the requirements put in place by NASA and the federal government are looking forward, right? When you start a new project, you are going to have to do this, assuming you're funded by federal funds. So this is kind of Andy's advice to doing open science, right? practice open science from the start of a project, not just at the end. It's going to be a nightmare. I've tried to kind of go back to data and software, and like, well, I need to send this to someone. You're just wasting a lot of time figuring out what you've done and changing the data in the software. So start practicing open science and kind of clean code, documenting data at the beginning of a project, not at the end. I think, within research groups, there's a lot of talk about overcoming the hero mindset, the scientist that does it all by themselves. There's a lot of effort involved in making data and software open. Open science is about collaboration. So if we're putting software out there, we can build on those software tools. If we're putting data out there, people can identify errors in that data and help us fix them. Share tools, tips, and tricks with your group or within your institution, right? The only way we're going to learn outside of a formal environment is if we work together and sharing information and knowledge that we pick up on the way. What works, what doesn't work. Don't duplicate work, right? This is still on the kind of sharing thing. Use collaborative tools. GitHub is a really wonderful way of doing version control on code and making sure that everyone can get access to the current version of the code. But you can use it for documents. You can use it for even small data files, although it's generally not used for data that can go somewhere else. But it's a way of doing version control. It's a way of communicating. It's a way of project management even. So it's worth taking the time to actually learn to use GitHub. And Matt Fisher has put together a great resource on kind of how to start that. Shared file systems for data. Don't have, if everyone in a project has their own set of data on their local machines, you're going to run into mistakes because you're not going to know what the most recent version is. And then document your workflows. Have a README file. What did I do to this data? What steps did I take? What code did I use to produce this plot? Documenting is going to really help you when you come to putting stuff out into the open. There's some simple steps we can take, right? There's a lot to take into advance. So shortlist possible practices for your project, right? You can't do everything, but you can focus on things that you're excited about or things that you help really going to move things forward. Consider what you can adopt yourself versus what the group needs to adopt. This is about both personal development as well as kind of changing the way a research group or an institute works. And then communicate with the research group about what to implement. Create an implementation plan within that group, and be flexible, right? Some things aren't going to work. Some things are going to work. This is a process, we don't have all the answers, so be flexible. And then document and share your best practices on what you did, right? You can give a talk on how you do open science on a particular project, not just presenting the results, or write a blog or something like that. And there's some ideas here in this paper here that I'm referencing, 10 simple rules for implementing open and reproducible research practices. I just picked what I thought were kind of the most relevant. Next steps that you can do today. If you don't already have an ORCID ID, get an ORCID ID. This is the way that you can, it's a persistent identifier, allows you to tie what you produce in research to you. It's your badge, and the way that research is linked to you. Get a GitHub account if you don't already have a GitHub account. Even if you're not going to start using GitHub, having it is useful because there are a lot of hackathons that use GitHub as authentication. And you can start dabbling, right? You can start playing around and learning. And as Walt said, register for the TOPS OpenCore curriculum. I did the Ethos of Open Science. It was a great 2.5 hours, lots of great discussion. It's very interactive, and I think you'll learn a lot. And then looking a little bit further down the line, identify a new skill to learn, maybe GitHub or Python, R or some other non-proprietary language, and start kind of building up that tool set for doing open science. And I think I'll stop there. I'd like to thank Ms. Steer and Mark for inviting me and Walt to talk about this. Hopefully it's been useful.